modulate, if you like, the basic inputs of people's activities and of weather, we have to then look at it in terms of how it operates within the technology within which we live. And now we spend roughly 98% of our time in the UK indoors. About 85% of our time at home, about 8% in buildings like this, about 6% in vehicles, and 2% of the time we spend outdoors. So this is fantastic change in humankind. We've all gone indoors, we've built this exosomatic apparatus, which, as you saw earlier, rather than needing 130 watts, we need about 5,000 watts to control this. Because now we have buttons, a button in your car which turns on 40 kilowatts of power, 40,000 watts. Turn on a boiler with 10,000 watts, we turn on a projector with 500 watts or something like that. All far, far more power than we actually need ourselves. So we have to try and understand how these people moving around and using these technologies, as modified by the weather, how that results in the demands for energy on very short time periods. If we look at a larger scale here, now we're looking at UK as a sort of mock-up of a future UK energy system. Now we have these big stores of gas and oil and coal, some of which we have still bits left in us, some now we're importing from Qatar or Ukraine, or not Ukraine, from Siberia, wherever. And we need to go to a future whereby in these centres here, we have the hourly changing demands for energy. And we're going to have to supply from these different sites like wind farms and hydro, maybe a bit of tidal power in the Severn Estuary. And we're going to have to try and match these demands, which are shown negative in this graph here, with the positive supply inputs. We need to match those two on a dynamic basis, and also taking into account the spatial variety, range. So now, instead of looking at Leviathan's physiology and its evolution over decades, we need to look at how to control this system over very short time periods. This is the smart grid kind of idea. And so in here we might have heat storage in our dwellings and industry and so forth. We've got heat storage here, which we can use in our district heating. Chemical store here with our fuels that we're making. A little bit of electricity storage here, pump storage, gas storage, and so forth. And they're amongst the components that we can control over periods of minutes and hours and days, and months even, in order to match the varying demands with the varying supplies. So one of the main ways that we can change the timing of flows, so the wind blows when it blows, and we want light, and we want light in here. If they're not at the same time, how do we try and match them up? And one way is with storage. And DynEMo at the moment models 7 kinds of stores. We have heat stores here in the domestic, service and industry sectors, electric vehicle batteries here, district heating store here, and this is synthetic chemical storage. This is hydrogen and ammonia, etc. This is our electricity system store here. It's tiny, absolutely tiny. We use a lot of heat, we use a lot of chemical energy. Those forms of energy are much, much cheaper to store than electrical energy. So I believe, apart from electric vehicle batteries, where it's integrated with the service supply in a car, that the electricity system storage will remain very small. It's too expensive.
Okay, what is the meaning of the running fabric storage?
Right, okay. On a winter's morning, something like 2 billion tonnes of brick warmed up in the UK, in dwellings and buildings. And to a certain extent, you can use the fabric of a house to even out your demand and supply. The problem with it is that it's uncontrollable. but it has a big effect on the dynamics. As we saw earlier in this house here, if you want a temperature at a certain time in this house, you turn the boiler on, but because of the effect of all the thermal storage in the fabric of the building, it takes some time to warm up. So the dwelling fabric and service sector building fabric here, I've just put it in, but it's not a controllable store. And only part of it will be electrically connected. So if you have an electric heat pump.
This is high thermal mass sort of.
Well, yeah, I mean, this actually is just not deliberately high thermal mass. This is just more or less the heat storage. If you take the whole building mass in the UK through 1 degree centigrade, you get about that much storage. It's about 2 billion tons of bricks. So, this is an impossible series of charts, but then you have this physiology, and it's like, you know, you've got your arms, and you need to look at all the energy demands and the flows with all the parts of Leviathan's body. So what we're doing here with DynEMo is it will model over any number of periods and lengths of time, but we're just looking at winter's day here. So we have a domestic sector there, just across the day. Here we are heating up the buildings in the morning. We have industry here, which doesn't vary very much. It follows the patterns of industrial activity. Service sector here, where this is heating on a winter's day. Very little heating in the industrial sector. And here's transport. So we have electric vehicles and electric railways. This is for 2050 scenario. And then we have district heating here, and our district heating can either be fed with electric heat pumps or with combined heat and power. When we have too much wind, we use the heat pumps. When we have too little wind, we use the combined heat and power. So it's a dual fuel system. And here, finally, we have our fuel synthesis, which is hydrogen and ammonia, operating across the day here. Now, each of these has a store. So these all have heat stores. Domestic industry and services. Transport has electric vehicle batteries. District heating has a heat store. Fuel synthesis has a big chemical store. So for example here, this is our district heat store temperature. So as we take heat out of the heat store to supply to houses, there we are, that's the heat coming out, the temperature falls. Then as we put heat into the heat pumps, it rises again. So you have all these different organs of Leviathan trying to be coordinated with algorithms which we've developed. And then we add all of these up, and we get total electricity consumption here. So it's domestic, services, industrial, transport, that's district heating, and this is the synthetic fuel store. So what we've done is gone from a pattern of useful energy demand like that for heat and electricity, for appliances and lighting. We've used storage for some of this useful energy so that we can come up with this profile of electricity demand. Why do we want that profile? Because it matches the supply of this here is wind power. So what we've done is use our storage to match fairly closely the profile of wind output. You can see it's quite a complex thing, so we're trying to develop algorithms which will control the whole system. It's not just electricity, you need to look at the control of the heat supply and switching there. And so this is a kind of, I think it's one of the frontier areas of research. And then we can look at it on different time periods and the dynamics of it. So we have a different picture here. Here we have our resources. This is the tidal power, wind speed, and so on. So again, we have this is solar energy. So we have our dynamically varying meteorology. And this results in this pattern of electricity demand here, where we have things like computers. Here's our electric vehicles being charged overnight mainly. Low temperature heat, high temperature heat, lighting. Okay, it's total demand picture. Here is our supply picture here, total renewable. So we have CHP, and onshore wind, offshore wind. And you can see here we have more renewables than need, because that's the demand. And so we export it to France, or we put it into batteries, or into heat storage. But here, we have too little supply for instantaneous demand, so we take heat out of our heat stores, we take electricity out of our batteries, and we import from France. So we're trying to balance it up dynamically as the time passes. And then, of course, this is changing day by day by day. So we're getting this complex variation that we will need to manage. And this is how we're going to have to become much more sophisticated in the management of our energy system. Because at the moment, most of our energy comes, need more energy, open a gas tap. Put more coal on the boiler. You know, put more oil in. But when we have a lot of wind and solar energy coming into the system, we can't control when it's going to come. So that's on day, but then also we need to look on longer time periods. So here we have winter, spring, summer, autumn again. Now we have our demand, which also changes with the weather, including wind speed. Here we have our supply across that period, dynamically changing. And here we have our heat and electricity storage levels, dynamically changing. And you can see that you might need to plan your energy storage over periods of weeks or even months. So, for example, you have this very large chemical store, so you think, well, let's make our ammonia and the hydrogen in the spring and the autumn. Because generally that's when we have most surplus of renewable electricity. So you need to plan over periods from minutes to days to weeks and to months. And in addition, of course, you have to coordinate. Here we have export of electricity here. So you have to coordinate with the French. France, of course, is connected to Germany, etc. We'll see about that now. Now, with these big machines, you can't just turn them on and off like that. The rotating part of a big coal-fired power station weighs 20 tons. It's a huge, huge thing. To start up a coal-fired power station with coal takes a day. So you can't just turn them on willy-nilly when you like. And so you need a very sophisticated generation planning model. So what we're looking at here, let's go back, is this is using now a rather sophisticated electricity generation model. So we have our demands here on a winter and summer's day. Each stratum is like lighting in commerce or computers or whatever, about 40 different demands. And here we have generation. Now in the UK at the moment we have maybe 300 generating units. And which can't be turned on and off. And as you turn them on and off, you get these great big lumps of energy you need to put in. And it costs money. So what we ought to try and do is manage our system. So if we have this profile of renewable generation, which we can't control, we're going to try and change the profile of demand such that the profile of demand will match that of renewable generation. And we'll do this using storage. It might be hot water tanks in your house, hot water tanks in industry. And as we're doing that, so this is an optimization going on here, and you can see that as we're changing the profile of demand here, using energy storage, we're gradually changing the profile of demand to match that of renewable energy, such that this energy, which comes from our big coal stations and nuclear, etc., is being leveled off. So that our marginal costs and emissions don't spike like they used to. So that we end up, this is a judiciously chosen example, we're using storage, we can exactly match the profile of renewable generation, and so our big thermal power stations are just running flat out all day long. Of course, you can't always do that. So there's various levels of sophistication you need to do this demand and load management. So if you expand out now, because time and space are conjoined in this. So when we look at the evolution of Leviathan, we started off, let's say, 2,000 years ago, when we lived in villages. And the village is a solar collector, so we had people living there, we had horticultural patches here, orchards here, we had big solar collectors here for our crops. And you notice that we're getting more distant from the centre of habitation here. And then there'd be self-propelled solar collectors like pigs going off in the forest and collecting acorns. And the radius of self-sufficiency of this kind of settlement might be of the order of 50 kilometres. Some things like iron, for example, would come from much further, but in terms of food, wood and so forth, it might be of that order. Now, in the world, we have our developed countries here. The population is pretty stable, and so is the number of households, although some increases we saw. In the less developed or poorer parts of the world, we're going to get this huge increase in population, a huge increase in the number of households, and more or less, it's like the equivalent of the population of the world in 1960 is going to be moving into cities in the next 20 or 30 years. It's huge. In China alone, 20 years, 300 million people will move into cities. And so, rather than having this localized settlement, we're now going to have these megalopolis, seas, where they're huge energy importers. If you look at, this is a cross-section across this idealized city here. Here we have the energy demand per watts per square meter, peaking in the middle where the density is very high. Here we have our potential renewable supply of solar heat and solar electricity into the city. And you can see that there's a huge deficit in the middle of these cities. So they will have to import from wave and tide, biomass, hydro, etc. from the outside. So instead of the radius of self-sufficiency of 50 kilometres, now we're talking about 20,000 kilometres. So London will import gas from Siberia. It's a truly global. So as the size increases, we're looking at increasing transmission over longer distances. And this has implication for time. Because of course, solar variation of the world, and indeed tidal power, is driven by the basic rotation of the Earth and its annual orbiting. That changes the flux of energy into the world. And then also, of course, with solar heating also changes, to a certain extent, the diurnal variation in wind speeds. And we are diurnal animals, so our activities, somewhat fortunately, basically follows solar energy. And so if you look at the energy consumption, here we have, as we're crossing with China and India and so forth, we get a huge bulge in energy consumption for particular hours of the day. Then as we cross the Pacific or somewhere, we get very low energy demand. So we can see here how space and time are enjoined in terms of energy demand and energy supply. And so one way we're coping with this is to have very large-scale transmission systems. So in Europe already, we have a pretty good transmission system which joins into Russia and it goes down into North Africa. And we can use this transmission system for renewable electricity trade. So if there's plenty of wind on the West Atlantic coast here, we might be exporting across into Ukraine, Russia, Greece, wherever. Or if there's lots of solar energy, let's say in Greece and the Mediterranean, we can export that up into Northern Europe. So we can use these large-scale systems to balance demand and supply from renewables. And one of the nice things about this in political terms is that it can go both ways. So that when we have too much here, we can export. When we have too little, we import. And so we have codependency. rather than one-way flows of coal, oil and gas from these big reserves in the Middle East and Siberia. So, this is the final slide. Leviathan's global electric future. We have this kind of distribution of population across the Earth, mainly in littorals, of course, but also quite large parts in the interior. This is not going to change very fast. I mean, the numbers will change, but the spatial distribution of these population centres probably won't change very fast. And of course, electricity consumption, or energy consumption, and here what we're seeing is a composite night view of the Earth, where this is lighting here, so it's a kind of surrogate for energy demand. Of course, it'd be rather unfortunate if the whole world was dark at the same time, because it would mean some cosmic catastrophe. And then at the same time, we have this, as the Earth turns, we're going to have this diurnally varying demand and supply. We have regular east-west diurnal and seasonal variations. So we have these two ways of matching demand and supply. One is storage, and the other is long-distance transmission. So you can even out demands and even out supplies. And in 1938, somebody called Buckminster Fuller said, why don't we have a global electricity grid? So this is a very old idea. I thought I'd come up with something new here, but of course I couldn't. And in fact, we already have a good grid in Europe. There's a very good grid, or pretty good grid in in the United States. Quite good grids developing in India, China, Japan, of course, very good. Australia, not so coherent. Europe is talking to Russia about reinforcing their grid connections. If we do that, then we're about a third of the way around the world. And so it doesn't have to be a sort of mega grid, something being developed, but just simply the gradual reinforcement and organic development of this system. Okay, stop. Thank you very much. Questions?
I have two questions, quite separate. First about CHP, that I read a survey that if all our cars in Britain have changed from petrol to biomass, it would need about double the agricultural land that we have in Britain, let alone if you started trying to do it in Europe and everywhere else, which sounds to put it completely out of the question. The second one is totally different, about how much can you get into our politicians, what you were saying, because they've just ordered 30 fossil fuel power stations, presumably will last until 2050, and spending all the money they've got. They cancel all wind farms. I think the news this morning was the final nuclear power station has now been cancelled, so there's none. Isn't that right? There were going to be 6 nuclear power plants with 10 reactors, and now there are none. I heard from the news this morning. I don't know if anybody heard better news than me. How can you get it into our politicians who are totally non-scientific?
Well, your first point is biomass is very limited. And in the scenarios I do, I assume that no more biomass will be available than exists now in terms of postal place of biomass. Because everybody wants biomass, and I can imagine importing everywhere. Nuclear power stations, these are political decisions in the end, because without central government underwriting insurance and investments in nuclear power, you won't have any nuclear power stations. And so this is really very difficult to determine how that will happen. All I will say is that I've been working this kind of thing for about 35 years, and this question hasn't changed.
Clive Oakroyd, Cranbrook University. We're looking at supply and demand and importing, exporting to France. Is there any work looking at changing things like working hours or the impact of, for example, staying 2 hours difference from the continent to actually smoothen out some of those differences?
Well, as I make the point with my rotating Earth, of course we have different time zones going around the world, and so depending on the time of year, there'll be an hour's difference or whatever in France, and so of course people do. This is one of the reasons you can smooth out demand. The further around the world you go, the bigger the time difference, and so the more smoothing out the demand you get. Whether I doubt whether there ever being deliberate attempts changing British summertime to -3 hours or something to help the coordination with France.
What about more locals in UK change working hours?
Well, certainly flexi time and so on might help the situation. But again, it depends. If we have lots of solar PV, for example, then you won't necessarily want people going to work, in the night. So it just depends. You have to look at the totality of the demand and supply and what's going on.
I guess there's a question about to what extent is this still, because there's a lot of assumptions in there about maximum behaviour change. At the moment we're really struggling with very minor behaviour change. There's a lot of political will required to implement any of this. It sort of seems to be a...
These scenarios are simply exploration. And for example, with aviation, it's saying, well, if you don't, if you no behaviour change, then really it's almost impossible to control global warming to any degree. And also to realise, by pointing out what behaviour change might do for you, like downsizing cars, for example, then people start to think about it, and then maybe they look to Norway, where if you want a big carbon-intensive car, it's fine, but you have to pay €70,000 tax to buy it. So there are these illustrations from the potential of the measure to how you might implement it.
Because one of the things that struck me was that there's going to have to be quite significant changes in industry structure to support some of the kind of process management side of this, because of the sort of increasing degree of integration that would be required to balance the supply and demand environment.
I think the impact on industry would be quite small, really. Maybe need a bit more, maybe a bit more insulation and some change of industrial activity. But it's not, we already make, Lord knows, however many gigawatts of gas boilers a year and so on. We have this huge investment in production of the energy system now, and okay, as I pointed out, it'll become more capital intensive, I think, but we'll be paying less for fuel. So I don't think it won't be unrecognisable.
And by industry sector, I'm talking about the kind of production and management of energy industry sectors.
Okay. Well, smart grid is the term of the last 5 years or so. When I started out, it was called load management. And we've been doing smart control for at least 50 years in this country. So it's not a new idea. It really isn't. And it's just, you have to become more elaborate. As we get more wind power and so on, you'll have to get more sophisticated. But it's really not rocket science.
Hi, 2 questions. The first is that some of this looks very similar to DEC's 2050 energy scenarios model. I wondered if you could say about how your assumptions on behaviour compare to the assumptions on behaviour that they allow you within their force with levels. And the second question is that politics is obviously a big question. Does this tell us anything about decision points? So at this point, if you have built a district heating network, forget about district heating as an option, or things like that to say, well, once you get to this point, you need to restrict what you think is reasonable.
Well, vis-a-vis the DEC calculator, I'm not sure exactly how detailed you can put in assumptions about behaviour change, like car downsizing or these models will say if you reduce the thermostat temperature by 1 degree, it will tell you how much less heat you need. So I don't think the DEC calculator goes to that level of detailed calculation. As far as I know, the DEC calculator doesn't look at the dynamic smart control detail. In terms of decision points, it's a difficult one. I've eventually come to the conclusion that you need to build lots of wind turbines. You want to try and make district heating schemes. You want to try insulating houses. These are things that we know are good. And do this for 10 or 20 years as fast as you can. And then it will become more apparent as we go towards the extremes what problems there may be in integration and so on. But to some extent, the very long term is almost doesn't matter very much. Let's carry on now doing what we know we should be doing as fast as we can. And what we can do is look at Sweden or Denmark or somewhere to get some view of what the future might look like.
Professor Rick Smalley advocated for sort of global, I don't know if you've heard of him, he won the Nobel Prize in 2004, I think, together with Quantum, for the development of carbon-60 as a long-distance transmission material, or at least the industrial process to create it in order to create something like small. I was just wondering if you knew of, I mean, he's since died, but whether or not you know of any developments on at least his advocacy.
I don't really. I mean, in terms of long-distance electricity transmission, we either have the alternating current, which is the main means we use, but if you want very long distances and the loss and the cost may be lower with direct current, when you go beyond, say, 1,000 or 2,000 kilometres, the balance of that it has other problems with direct current for transporting voltages, for example. What the optimum balance will be, I really don't know. When you're connecting up systems with different voltages and frequencies, of course, you have to go through a direct current phase. In terms of new materials and technologies, pretty ignorant.
The other thing to note is politically, I mean, dependency also brings up, I mean, for us to be the Saudi Arabia of energy, Europe might mean that even the West goes down here to be able to deliver. I mean, it's still the kind of Kissingerian sort of codependency idea that will lead to peace doesn't necessarily really apply. I mean, it's of course there will be some regions that have independent advantage over others, and that's definitely kind of my elephant in the room when it comes to this particular debate.
Yeah.
But I mean, just to comment on that.
Well, when you look at the world, of course, we've got this fantastic concentration of oil and gas in here, and of gas up in Siberia. And so it seems to me, if you had bidirectional exchanges, maybe not of the same field, maybe it would be renewable energy coming one way and oil coming the other way, I don't know. But the more exchange and codependency there is, the less likelihood there's going to be of going to war.
But the idea would be to move away from those non-renewable forms,
well,
which will leave certain countries.
As I pointed out at the beginning, we have no choice. Very good time. It's just how much frack gas and oil shale, how much time that will buy us. But when you look in the long-term scheme of things, it's quite a short period. And so I think we should be trying to develop towards this long-term future as fast as possible, because I think it is more politically secure, and maybe before too long it will be lower cost to us.
I think the lower cost is definitely the thing to sort of really settle on, because it's at that point, the volatility is more the issue.
Last three questions. Michelle over there, and then two questions here. So Michelle?
Michelle should go to UCL-Energy Institute. That was great, thanks Mike. There was a paper produced a few years ago with Proceedings of the National Academy of Sciences that compared, so looked at the potential, if you like, of household emission reduction in various technological and behavioural options, and compared that to the empirical